Hello, everyone. My name is Fiona Bell, and today I'm going to be presenting the paper Shape-Changing Clay Dough, Taking a Material-Oriented Approach to 3D Printing, co-authored by Erin McClure, Camila Friedman-Gerlicz, Ruby Ta, and Leah Buechley. All clays inherently shrink when they chemically transition into ceramics during the firing process. Inspired by clay's natural ability to change shape via its shrinkage, we developed a material called clay dough to enable dramatic, tunable shrinking behavior. Clay dough is a 3D printable material that is made from a mixture of stoneware clay and corn flour dough. To make clay dough, we combine WH8 stoneware clay with a dough made from corn flour, wheat flour, vinegar, vegetable oil, water, and optionally food dye. Previous versions of this dough was developed by Buechley and Ta for the purpose of 3D printing with a sustainable material. However, this recipe was never fired. We alternatively use the dough to enable more dramatic shrinkage of ceramics during the firing process. In this work, we use the following clay dough recipes. We first use pure clay, meaning that the recipe contains 100% clay and 0% dough. We then use recipes containing 75% clay, 25% dough, 50% clay, 50% dough, and lastly, 25% clay, 75% dough. For clarity, I will refer to each recipe by the amount of clay present within it. We also color code these recipes with food dye to make them easier to track through our design process. We find that each recipe shrinks a different amount when they are dried and fired. To determine the shrinkage of each recipe, we 3D printed small hollow cylinders and tracked their measurements as they proceeded through each drying and firing step. The cylinders shown here are what they looked like right after 3D printing. We then dried these cylinders in a dehydrator and found that all the recipes shrank slightly due to water evaporation, with clay shrinking the least amount and all the recipes containing dough shrank more so. Once the cylinders reached a bone-dry state, they were bisque fired in a kiln. Bisque firing occurs at a relatively low firing temperature. During this firing stage, the dough burns away and the clay chemically transitions into a ceramic. This causes much more dramatic shrinking to occur. Lastly, we glaze fire the cylinders. Glaze firing happens at a higher firing temperature and is the phase in which the ceramic fully vitrifies, meaning that it gains a more glass-like and crystalline structure. After this stage, the material reaches its final maximum amount of shrinkage. Through this test, we ultimately correlated the amount of dough to the amount of shrinkage that occurs. Beyond shrinkage, we further characterize other material properties such as density, porosity, and strength of each clay dough recipe. I will not go over these results here, but I encourage people to read the paper if you are interested in learning more. Through all of this testing, we gained a deep technical and embodied understanding of each clay dough recipe, which led us to our material-oriented approach. Our material-oriented approach is where the form of the ceramic artifact is physically driven by the material's shape-changing properties as opposed to physical actions made by the human maker or the 3D printer. We exemplify this approach most directly through a collection of cylindrical vessels that are designed by selectively placing clay dough recipes within the 3D print. This process begins with sketching the silhouette of the envisioned vessel and mapping it to each clay dough recipe. We then cut out the resulting material pattern and adhere it to our print tube. We then fill the print tube according to the pattern with our clay dough materials. We then attach our print tube to our 3D printer. For this work, we used an Ezhou Zero, which is a widely available small-scale clay 3D printer. We then used an open source software library within Rhino and Grasshopper to design a large cylindrical vessel. The software library bypasses the need for slicing softwares by directly generating G-code that can be uploaded to our 3D printer. We then print our cylinder. As you can see here, the extruder is moving in a sine wave to create a nested wall. This is to promote structural stability of our large cylindrical vessel. Once printed, we can see how the cylinder shrinks into a new form after it goes through the drying, bisque firing, and glaze firing steps. We use this method to explore how the same cylindrical model changes into a range of different forms using basic material loading patterns like halves, thirds, and fourths. We also use our material-oriented approach to produce more complex ceramic forms that matched our originally designed silhouettes. By further thinking about how material placement within a print can develop form, we began to explore non-cylindrical forms, such as this plate that changes shape into a bowl. We intentionally printed this plate with 100% clay at the bottom, 75% clay in the middle, and 50% clay on the top. As the 50% clay shrinks more than the 100% clay, it pulls the edges upwards and inwards into this new bowl-like form. In contrast to intentionally controlling shape change, we explored more randomized patterns by reusing our scraps. The purpose of this experiment was to not only reuse our waste for sustainability purposes, but to probe what it would look like to have forms that are entirely driven by the clay dough materials themselves. This ultimately resulted in unpredictable vessels that we did not directly design. We continued this line of exploration by printing more complex 3D models, such as this teapot, with our random scrap materials. The teapot on the left is printed from 100% clay and closely resembles our model. Meanwhile, the teapot on the right is printed from the random mixtures of clay dough, which deformed our intended design. This unpredictability of clay dough also led to many forms that we deemed as failures because of how they cracked and collapsed upon themselves. However, we see these unpredictabilities as the agency of the clay dough shining through in this work. In turn, we view these failures, as well as the shrinkage of clay dough in general, as a mode of unmaking, wherein which the clay dough is literally unmade by the dough burning away during the firing process, thus leading to the form of the ceramic being remade into something new. We envision this conceptual understanding of clay dough's shrinkage generating new interactions with shape-changing ceramics in the future. We also envision clay dough benefiting people who do not have fluency in CAD or CAM softwares. This is because our material-oriented approach acts as a making process that employs digital fabrication but does not require computer-based tasks, meaning that we can design complex forms through material selection rather than software-based tasks. In contrast, we, the authors, as experts who are familiar with CAD and CAM softwares, found that Clado sensitized us to the importance of materiality and material agency in digital fabrication, which we find is often overlooked. In turn, we found ourselves engaging with Clado in an incredibly intimate, mindful, and generative way. Thank you all for listening, and I would like to invite you all to reach out online if you have any questions.